Welcome to my CompTIA Security Plus lecture review. Here we're looking at the textbook CompTIA Security Plus Guide to Network Security Fundamentals, the 6th edition. We are covering the SY0-501 Security Plus exam. Here's the ISBN number for the given text. My name is Arthur Solomon. I'm going to be working with you throughout this video lecture. One of the important things that I did want to point out is I am using this textbook, which is published by Cengage. All of the rights are reserved by them. This is just a video lecture of me going through the PowerPoints, assuming that you are in my Security Plus course and you've already purchased the textbook. Keep in mind, I'm not covering every exact section of the textbook. I'm just covering highlights of the official PowerPoints produced and owned by Cengage. Chapter 4, Advanced Cryptography and PKI. So the objective of this video is looking at cryptography systems, more of the advanced systems, defining digital certificates, looking at components of a PKI, public key infrastructure, and we're going to describe the different transportation encryption protocols. So let's go and jump right on in. So cryptography that is improperly applied can lead to vulnerabilities. When we assume that cryptography or encryption is there and it's functioning without ever verifying or testing, leads to vulnerabilities. I've actually encountered several attempts where we were setting up VPN technologies and we thought the VPN was using AES, but in reality it was using 3DES. Both of those are symmetrical key encryption algorithms. However, triple DES is easier to break. And it turns out that another third party had configured the encryption type, and we were just going off of their config file. However, once we realized that we were doing triple DES, it actually led to a vulnerability assessment, which it turned out that we were actually leaking data. So again, verifying the cryptography and encryption systems are crucial. We cannot assume that they are operating one way without them being tested. It is essential to understand the different options that are related to the different cryptography systems. If we're dealing with a VPN, are we looking at phase 1 or phase 2 of the VPN? Are we understanding the handshake process? Are we understanding the algorithms that are used in that process? Do we understand the key strength, the secret algorithm use? Are we using different types of ciphers? Are we using a block cipher? Are we using other forms, a stream cipher? Are we understanding the operations of the different ciphers? And again, we also have to understand the algorithm input values and export values and understand if there's any weaknesses tied to those algorithms. A weak algorithm exists. Us not using current standard algorithms can result in data breaches or data leakage. So there is a difference between encryption and properly implemented encryption. So let's go ahead and let's look at key strength. So a cryptography key, it's a value that serves as an input to the algorithm that transforms the plain text into ciphertext, or vice versa, depending on if you're encrypting or decrypting. So the key is going to be used as the mathematical input for the algorithm. Three primary characters that must be determined: the resilience of the key, this is also known as the key strength, the randomness of the generated information, the length of the key, and the crypto period. The crypto period is the length of time in which a key is authorized for a user or an individual or algorithm to use. Keys have different lengths. Again, that second bullet point, length of key. Also, that length of key has to be able to be randomized. So here we have a key length, 3, 4, 5, 6, and so forth. And so a key length of 3 has essentially 17,000 and some change key space. That means the average number of attempts needed to break that key space is just under 9,000. And then as the key length increases, so does the number of attempts. Needs the number of attempts in order to break it. You'll notice for a key length of 8, we're looking at 208 billion key spaces. And that means we're looking at 104 billion attempts to break those keys. The secret of the algorithm. Would a secret algorithm enhance the security in the same way as a key or password? No. These algorithms are pretty open standard. You can go and you can see the mechanisms used, the formulas used to actually create the encryption. But for our cryptography to be useful, it needs to be widespread. Users have to know about it. For example, a military force that uses cryptography means everyone that's using it must know about it. Alexander the Great, good example. As he passed messages throughout his empire, anyone that would be receiving the message had to know about the message, how to decode or how to encode those messages. Julius Caesar, same way. Nazis with the Enigma machine, same thing. Understanding of how the encryption works must be widespread in order for the use of that crypto system to be used. So, operation modes. So I know right now we're looking at predominantly block cipher modes, but this is only one type. So we're going to talk about other block modes a little bit later in this lecture, but not as detailed. So here we're looking at the block cipher modes of operation, and again, this is just how the block cipher manipulates the entire block of text in a single pass. The plain text is again chunked up into segments, blocks of a specific length, and then each block is encrypted independently of one another. The block cipher specifies how the block cipher should handle these blocks. There are 4 common types of modes: the electronic code book, the cipher blockchain, a counter, and a Galios counter. These are the 4 main modes for using block ciphers. So let's go and let's look at some of these crypto service providers. So a crypto service provider allows an application to implement an encryption algorithm for execution. These are the service providers for those algorithms. Crypto services provide basically implementation of the algorithm. They will help generate the keys, they will provide the key storage and distribution, and they will authenticate users by calling various crypto modules to perform specific tasks. Again, this is all generated through the algorithm and its functionality and the modularity of that algorithm. The crypto service provider is implemented through both software, through hardware, and a combination of both. So it really just depends. So, example, Windows 10 has a crypto service built in. The service is called the cryptographic service. So this is one of the more important aspects of this lecture. Cryptographic algorithms do require additional information to key values. Sometimes these algorithms require specific input values. Salt is a good one. Salt is a value that can be used to ensure that plain text, when hashed, will not consistently result in the same digest. So if we're afraid, for example, that our password might end up being in a rainbow table, if we keep generating the same content, the hashes may become known, and we can actually reverse a hash to find the original plain text. So what we can do is we can add a salt. That way the salt will generate additional hashed values when it actually goes through the calculation. So if we take a value and a salt, our digest information should be different. This is most often done in passwords. Here, the password would actually have to be decoded and use the correct password. The system would not allow for a hash to be passed for password purposes, because again, the hash would be different with a salt. The nonce is an input value that must be unique with some specific scope. The initialization vector, the IV, this is the most widely used input for our algorithms. This is going to be our initial vector, our initial numbering scheme. So moving forward, we have our digital certificates. This is going to be one of the most common applications for cryptography is our digital certificates. This is used to verify one's identity online or on a network. So how do we use a digital certificate? First of all, we need to understand what they are, how they work, how they're managed, and determine which type of certificate is appropriate for certain situations. Not all situations are going to use the same type of digital certificate. So a digital signature, slightly different than a digital certificate, it will be used to provide a document originating from a valid sender. For example, Adobe has the ability to have a sender sign the document, thus allowing someone who receiving the document to verify that digital signature, ensuring that you trust the signature of the source. There are some weaknesses for using digital signatures. They only showed that the private key of the sender was used for the encryption in the digital signature, and imposters could post a public key under a sender's name, and that leads to additional issues. The problem is when we're dealing with digital signatures, the actual signature is going to be encrypted using asymmetrical key. That's going to be the private key. So here's a good example of how digital certificates are used. Bob will create a real message, and Bob will have a public key. We have some form of man in the middle who will receive the message and then will generate a different key. The man in the middle may then forward on an additional message, and the destination will receive the message and will use the imposter's public key to decrypt the message. This is an example of man in the middle using these types of digital certificates. That's what makes this a little bit more complicated when we're dealing with key distribution. So we have to have trusted third parties, and this is used to actually negate some of these key distribution issues. It will verify the owner and that the public key belongs to that owner. This is all part of the public key infrastructure. This helps prevent man-in-the-middle attacks, and it helps prevent impersonating owners' public key or the generation of a new public key by an imposter. A digital certificate is the technology used to associate a user's identity to a public key that has been digitally signed by a trusted third party. Alright, so how does this actually get used? How is a digital certificate used? So here we have Google. We actually have HTTPS that has a digital certificate and it is signed. We trust this certificate. We trust this certificate right here. It is issued by GTS CA, CA being a certificate authority, and that's being issued to Google. We trust Google because we trust this certificate authority. If we mouse over this a little bit more, GTS is called Google Trust Service, and they are Global Sign Root Certificate Authority. There are certificate authorities out there that actually sign the certificates. We trust the certificates because we trust the issuing party. So several entities and technologies are used to manage these digital certificates. The big one is certificate authorities, the top level guys that issue these certificates. They provide the tools for managing these certificates. A top level certificate authority is also called a root certificate authority, and they are responsible for all digital certificates underneath them. If a user wants a digital certificate, they have to generate a public and private key. The user must complete a request, typically known as a certificate signing request, CSR, and the user must then electronically sign the CSR and send it to an intermediate certificate authority. Individuals don't deal with certificate authorities. We deal with regional or intermediary certificate authorities. They will take our requests and they will process. They can act on behalf of a certificate authority. Think of it as a giant hierarchy, essentially. We deal with the guy 3 or 4 levels down. So let me grab my pen. So here's the top. Here's the intermediate. Here's another intermediate. Here's another intermediate. And here's another intermediate. Well, we deal with the guys that are down here. They can act on behalf of the root, but we don't get to interact directly with the root. There's only so many root certificate authorities, and I mean, they deal with massive amounts of requests. That's why we individuals deal with the ones that are down here. Big businesses like Google, for example, may actually interact with the root certificates. Keeping in mind, we just looked at Google's website, and Google certificates are issued by the Google, the GTS, which is owned by Google. So I mean, they have enough money to pay for their own certificate authority. But we essentially send our intermediate certificate authority our signing request. They go up the chain, they get approval, it comes back down the chain, and then we're allowed to be issued our certificates. So here's a few examples. For example, like a car title. So we will apply for the car title application. That's essentially us doing our CSR. We have to sign the car title application. That will be us affixing our public key to our certificate, verifying who we are. We may have to send the paper to the county courthouse. That is, again, equivalent to us actually contacting a intermediate certificate authority. The courthouse will process their request, and then they will send it approval to the DMV, and then the title will be sent from the DMV to us. We don't get to interact with the back end DMV. We interact with the courthouse that releases the information from the DMV to ship it to us. That is the same situation with the digital certificate. We act with the intermediate. The intermediate allows the certificate authority to send us our certificate. We don't interact with the certificate authority directly. So intermediate certificate authorities are, again, subgroups, and they're designed to handle specific tasks. Normally the task is processing those requests and verifying the identity of the individuals making those requests. The person requesting the certificate, you can authenticate based off of an email, a document, personal information, business information, web content. It really all depends on the level of verification. Now, the fun part is, if I create a domain, I can actually have a certificate issued to my domain by providing an email address. Well, that's really not super trusted. However, things like Google, Wells Fargo, Bank of America, big companies actually have to go through a much harder process to have their certificates actually verified, because there's also some backing there. There's more information that's required. There's more money involved. And those typically are going to be personal contact information, verifying business licenses with business requests, things of that nature. All of that is to ensure the security and the integrity of those digital certificates. A common method for ensuring security and the integrity of a root certificate is that it stays offline from a network until it's needed. It is only brought online when a specific need is there. So now that the certificate authority has issued the certificate, what happens? We end up with a certificate repository, CR. They are publicly accessible, centralized directories of digital certificates. This is how we can verify those digital certificates. They can be used to view the status of those certificates, to ensure that the dates are correct, that the names are correct, that the domains are correct, things like that. And they can be managed locally by setting it up as a storage area connected to the certificate authority server. What's interesting here is we also have a certificate revocation. This is a list of certificates that have been revoked. Reasons certificates are revoked are typically they're no longer valid. The dates are no longer correct. Details of the certificate have changed, such as maybe the address or the domain name, or a portion of the domain name has been modified, things like that. Lastly, the private key has been lost or exposed or suspected of those areas. That will create a certificate revocation list, CRL. And this is a list of the certificate serial numbers that have been revoked. Each certificate actually has a serial number. So again, all I did was I went to Google, looked at the certificate. We've already seen this. If we go to details, we can see a serial number for our certificate. And again, we can see the issuer, we can see the version, we can see the valid from, to, that will be the end date at that specific time. Once it is 1:07 a.m., this certificate is no longer valid. We can see things like the name. This certificate only applies to www.google.com. This does not apply to any of the subdomains of google.com. And again, there are things like the authority key issuer, who we got it from. The alternative names, again, this is only for www.google.com. Here we have our CLR distribution point. This will actually show us our CLR list. If you go to this URL, you can actually download the CRL, and you can actually see the certificates that have been revoked. And these are all for Google. Again, typically they're revoked because of the date. But this is what the CLR looks like. It's just a list of revoked information, and we got that from the digital certificate. So, certificate management. If we're looking in Windows, Windows has a cert manager. You have the traditional root certificate authorities like VeriSign. You have the big companies already trusted in Windows, and so you'll see that they're already here in Cert Manager. In the CRL, you should see one for through VeriSign. That's pretty common, since VeriSign is the big root certificate that we get a lot of that information from. So if we're talking about certificate management, we have an Online Certificate Status Protocol, OCSP. Essentially, this actually does the real-time lookup of certificate status. So you don't realize what's happening behind the scenes when you go to a website. The digital certificates are being checked and verified, even though it only takes a split second for these verifications to occur. This process is called a request-response protocol. It will go out, verify, check status, and return. If it is a valid certificate, it will carry on. If it's an invalid certificate, we may get a warning message. So the OCSP will actually have a sampling, which is a variation of the OSCP, where the web server sends queries to the appropriate OCSP responder server at regular intervals. So instead of having to request them, we can get an up-to-date list that way. So these are called stamped responses. So essentially, we're on a web browser. We want to go to, let's say, Google. We send the information to connect. The web server has to verify the certificate is valid. The OCSP will actually give the approval if it's valid or not. The web server will respond with it's valid and approved, and we can then view the website. That's on top of all of the other network communication functions that are there. So when you go to Google.com, you have the DNS query, you have the DNS lookup, you have the HTTP GET request that retrieves the website. But then one step further, since we're using HTTPS, not only are we having to do a GET request, we're also having to look up the certificate to verify the authenticity of the certificate. So you start seeing how this process is actually more complex than initially reviewed. All right, so there's different categories for digital certificates. We have a root certificate, we have a domain certificate, and we have both hardware and software certificates. We also have a self-signed certificate that's not listed for some reason, but that's also a common type of certificate depending on the organization and how you're using certificates. So a root digital certificate is going to be the top level. And this process of verifying the digital certificate is genuine depending on who is the root. There is a chain that documents the trust. If we trust VeriSign, and VeriSign signs a certificate for Komodo, then we trust Komodo because we trust VeriSign. Well, that's chaining. If Komodo then trusts another third party, then we trust them. So the beginning point of the chain is called the root certificate. Here's an example. Equifax might be the root certificate. We may have an intermediate digital certificate. There's still a certificate authority, but they are intermediate certificate authorities. We trust the top layer. They trust the subgroup, so we trust all the way through. When we go to the actual domain, buyonline.com, we get a user digital certificate, but that user digital certificate has a chain showing the trust model, showing the trust. And here it was an example of our certificate path. So back to Google, back to our lock, back to our certificate, our certification path. We trust Google Trust Service. Google Trust Service trusts GTS CA. GTA CA trusts Google.com. So we trust Google.com because we trust that top layer, that root level certificate authority. And in reality, it's all Google. Google owns all three. But again, they're large enough where this is more appropriate. We've already looked at information like the public key. We've already looked at the signature algorithm. We've already looked at the issuer and the valid to and from dates when we looked at the Google certificate. So the second common type of digital certificate is a domain digital certificate. And this most digital certificates are web server web-based. They're issued from a web server to a client. These are certificates that are issued for web content. So the web server digital certificates perform two big functions. They ensure the authenticity of the web server, and they ensure the authenticity of the crypto connection to that web server. You go to wellsfargo.com. Well, as long as it has an HTTPS, that lets us know that there's a digital certificate being applied. One, that lets us know the digital certificate that is applied, who trusts, who's the certificate authority that is there issuing that certificate to that trusted individual. And two, that lets us know our connection between our device and that web content is also then secured. So again, that's how that twofold authenticity functions. Do we trust the web server, and do we trust the connection to that web server? There are several types of domain certificates that are out there: domain validation, extended validation, wildcards, and subject alternative names. So, if we're dealing with email systems, they mostly deal with SANs, subject alternative names. So I may have three different names for my email server. I can list them as different alternative names on a certificate. Not just google.com, but I may have www.google.com, star.google.com, about.google.com. All of those are subdomains of google.com. Well, I could use that as a wildcard. So instead of having a certificate for each one of them, or instead of listing each one of them as a subject alternative name, I could have just star.google.com, and that way it will take all domains underneath the primary google.com's domain. Alright, so I tried going to Gmail or mail.google.com, but it does not like Internet Explorer, so I can't do that. So I have about.google.com, I have www.google.com, and I have workspace.google.com. Looking at their certificates, each one of them has a single domain, about.google.com. This will have www.google.com. That means these certificates are issued for that domain only. There is no additional subject identifier, nope. Signature hash, nope. So this is only issued to that domain. That's it. Workspace.google.com is issued to star. The domain is actually a wildcard. That means this certificate could be issued for all three sites and still function. The subject is anything at google.com. So instead of having multiple certificates, we could have just this one certificate, and that would also work. So when we're looking at all the tabs, wildcard's going to be that star.domain. That means all subdomains. We could have one certificate per domain if necessary. The first two certificates, that's what they were. They were directly pointed to about.google.com or www.google.com. Those were domain specific. And there's pros and cons for those, but realistically, cost is always a better motivator. A wildcard's more expensive, but that means you can apply it to more devices. So how does a domain certificate function? So again, we have a web browser and a web server. The browser will send a client hello message, and that will also set up the cryptographic information. The server will send a server hello response, and that will be the algorithm supported as well as the digital certificate. The browser has to verify the certificate, and it will create a pre-master secret. That basically is just a way for us to begin a exchange of information. That then will serve as a client key exchange, sending the web server our master secret. The web server will create its own master and its own session. It will respond, and it will actually have compared itself with the master secret and session key of the web browser and the web server. If they are the same, secured communication has been verified and data will be sent. Domain validation typically will have like a lock or a green checkbox or some type of denoting that the website is secure. Typically, the lock is one of the most common ones. And here we have, again, Google that we've been using. Some domains will actually require extended validation. This is a type of certificate that requires more extensive verification and legitimacy of the business. For example, Twitter pays for the extended validation. That means not just anyone can request these certificates. It requires a specific level of management to get involved. They have to verify who they are. They have to verify they can speak on behalf of that business. But there's also way more money involved at this type of certificate. We've already talked about domain names. We've already talked about wildcard domain names. We've already talked about subject alternative names in use of digital certificates. Again, if we're using email, other forms of unified communication certificates, UCCs, will be using those SANs. And again, that's just a clever way of saying multiple names attached to a digital certificate. That's all that is. We can have hardware and software certificates, which we've already talked about, machine, code signing, email signing, and so forth. All right, so digital certificate formats. Certificates come in multiple formats. You can have a International Telecommunication Standard certificate, the ITU certificate. You could have a X509 standard. While X509 certificates follow the traditional standard, they also allow for different types of encoding. Basic encoding, canonical encoding rules, and distinguished encoding rules. Realistically, I see CER types encoding as one of the most common methods that I've seen in real world. This is just a clever way of showing that certificates come in multiple ways and they can be applied in multiple ways. Basically, what we do is we will take the management tool for the different digital certificates or the appropriate cryptographic system, and we import the request, we import those certificates, and we verify those trusts. Interesting for that is that starts building out our public key infrastructure, our PKI. So in order to get more involved with our PKI, we need to understand a few things. We have to understand how PKI is managed, how key management is performed, and how that trust model is involved. So keep in mind that the PKI is used to distribute and manage digital certificates. Because again, there has to be a consistent means to be able to handle all of this. So the PKI is a framework that handles it. The certificate management action facilitates by PKI allows for the creation, the storage, the distribution, and the revoking of those digital certificates. So we've already talked about trust, and we kept saying the word trust models. So what are trusts? Trust is confidence or the resilience on another person or entity. The trust model refers to the type of trust relationship that exists between two entities. Direct trust is a type of trust model where one person knows the other person. One entity directly knows the other entity. A third-party trust is two individuals trust each other because of a trust in a third party. We trust VeriSign, so we trust anything that VeriSign signs. That's a third-party type trust. We trust Google, and we trust anything that Google signs is also a third party. However, when we trust Google and Google signs other Google things, we trust them because there's that direct trust. This is called a hierarchy trust model. And again, we've already looked at a root certificate, and we trust things below them because we trust the root. This essentially allows a single certificate to have a private key that can be compromised, rendering all certificates below it worthless. So that's an issue with the trust model. Having a single certificate authority who must verify and sign all certificates may create some issues. So here we have the certificate authority. They have multiple public keys for each private key that they have. But in reality, a better model is what's known as a distributed trust model. We have certificate authorities that are able to grant digital certificates. However, they don't. They actually allow their intermediate certificate authorities to grant those certificates. The intermediate certificate authorities will generate their own keys on behalf of the certificate authority. So the certificate authority will generate their own private key. They will then share their public key with their intermediate certificate authorities. The intermediate certificate authorities will take the public key from the root certificate authority and will incorporate that in their generation of their own private key, and they will use that to sign the certificates below them. That way, we're still doing it based off the trust of the certificate authority. We are just distributing that trust so that if a intermediate certificate authority does get compromised, we don't compromise all of the certificates that fall below them. Another type model is called the bridge trust model. And essentially that's where one certificate authority acts as a facilitator to interconnect all other certificate authorities. We can have major certificate authorities, Google and VeriSign, and we could have a certificate authority that bridges between those the root certificate authorities. That is called the bridge certificate authority. And that's actually what a lot of organizations end up doing. Keep in mind, these root certificate authorities are large corporations. They're not mom and pop. So this implementation and this management is extremely expensive, but these services are done by these organizations as an operational cost. All right, so moving on, let's talk about how we manage the overall PKI infrastructure. We have certificate policies, CPs. These are published rules that govern the operation of that PKI. It can also provide the baseline for security requirements. We also have a practice statement, and this is more of a technical document that explains how the certificate authorities use and manage their certificates. This also will encompass the registration, the revoking, the issuing, and the overall procedural controls for key management or key pair management. It goes through the life cycle of the keys: the creation, suspension, the revocation, the expiration, and the entire process all over again. So key management focuses on things like key storage, usage, and handling procedures. Storage is going to be one of the big ones, and that's going to be, how do we actually store public keys? Well, we can embed them with digital certificates. This means the private key storage, they're going to be stored on local systems. Software-based storage will expose the keys to attackers, so there's some issues there. So an alternative to storing keys in hardware, it's going to be hacking that hardware, like a smart card or a token or an RFID card, and that will actually have the keys in the card, thus not having the key attached to software storage. Software-based storage is attackable. Hardware storage is still attackable, but you have to have physical connection with that device, so it makes it a little harder to steal. Key usage. This is where we have multiple pairs of dual keys that can be created. Keep in mind, in an asymmetric system, there is one private key, and there could be multiple public keys. But for each conversation that is separately encrypted, it's going to have a different private key. These are called key pairs. And one key pair is used for encrypting the information. The second pair is used for digital signatures. So, again, there are multiple key combinations depending on the purpose. This is what gets into handling procedures of these key pairs. We have what's known as a key escrow, and this is where keys are managed by a third party, such as a trusted certificate authority. These private keys are split and each half is encrypted. That way, not the full thing is stored in one location and is less susceptible to brute force attacks and other types of theft. The two halves are sent to the third party, which is stored each half in separate locations. That way, in order to breach a key, you have to have two different locations breached, not just one. Part of the error handling or the key handling is also going to be expiration and renewal. The expiration is tied to the date. The renewal will be a renewing process for the existing key. That also includes things such as revoking the keys, recovery of the keys, if the key is lost. This is known as a key recovery agent, and this has to be set up prior to the keys being lost. You cannot have a recovery agent take place after you lose a key. We can also have a group of people that can be used for recovery, not just an individual. I always recommend when you're securing something via encryption, set up the backup key or recovery key. That way, if the primary key is lost, you can still access the data. I have had incidences where I've encrypted data, lost the key, and then lost the data because I lost the key. So a recovery agent is pretty important and pretty a big deal when you first set up your encryption, just in case you lose your key. We also have to understand that within our handling, we have to have a way to suspend a key. And when we suspend a key, we have to understand the process, the time frame to either reinstate or to destroy. If we destroy the key, we have to have the ability to remove it off of all systems. And that means removing all public and private keys from the appropriate authority. And that includes adding it to the revoke list. So here we have multiple parts. We have multiple groups. This is part of that N plus M group. Instead of having a single recovery agent, we can have it spread against multiple individuals. It really all depends on how you want this done. So, one of the last major things we have to talk about is transportation protocols. How do we actually make sure that our cryptographic transportation algorithms are actually being used? The big ones are things like SSL. We've seen that when we went to Google, we had HTTPS. Well, that S is secure, and we do that via SSL. SSL comes in 4 main flavors, 1 through 3, and we have an SSL layer 4, version 4, that became known as the Transport Layer Security, TLS. That is the new level of encryption that we are all using. We have other protocols that are used in communication, things like SSH or HTTPS or secure real-time transport. Those are all dealing with the transportation of data. So it really all depends on what we're trying to do. That builds into the understanding of how do each of these technologies actually secure the data. SSL uses a common type of transport algorithm. It was developed by Netscape a long time ago. We had AES using SSL, and you will notice that SSL version 3 was the most current version, but I just said SSL version 4 was the most current version. Transport Layer Security, TLS, actually took SSL v3, and that was the base for TLS version 1. I've seen several cryptology books that use SSL v4 as the common name for TLS v1. So it really just depends on the text that you are reading. TLS has newer versions. There's now version 1.2. And again, each newer model of our SSL or TLS just means better security implementation. That's all. And that means the removal of older variations of SSL when they become weak. So we have this thing called a cipher suite. And this deals with the message authentication code, MAC, M-A-C. And this is the algorithm that is used with both SSL and TLS. So how do we determine the appropriate length of key for security? Well, right now, our current baseline is a key of 2048 bits. Anything less than that is weak. Ideally, you want to use 4096 bits or larger. That defines our stronger levels of key. SSH, which we've already talked about, a communication protocol. This is used to remotely access a PC or a device. This replaced Telnet because SSH actually encrypts the data being transmitted. SSH actually has several different types of login and several different versions, SSL v1 and version 2. The SSH is actually a suite of utilities using slogin, SSH, and Secure Copy Protocol, SCP. And this uses digital certificates to verify one's identity before starting the encryption process. HTTPS, again, this is going to be the secure version. HTTP is used for just plain text. When we are dealing with HTTPS, that is going to be sent over SSL or TLS, depending, and it will use port 443 instead of the plain HTTP uses port 80. And again, you can always see the HTTPS, and you'll know that's secured, and that's secured communication over port 443. SMIME is going to be Secure Multipurpose Internet Mail Extension, and this is about being able to send email securely, and this will be done via a digital signature. We had our other communication protocols, the Secure Real-Time Transfer Protocol, SRTP, and this is actually using VoIP. This is used for VoIP and video conferencing. All this means is we add the security feature of the message authentication and confidentiality functions for VoIP communication. That way we can verify source and destination of the stream of communication that's coming along. Lastly is our IPsec, or IP security. This is a VPN-based technology and is considered to be transparent. That means It is transparent to applications, users, and software. It provides authentication, confidentiality, and key management. It supports 2 forms of encryption: transport, that will encrypt only the data portion of each packet, and it leaves the header unencrypted, or tunnel. The tunnel will encrypt both the header and the data portion. And that is it for this chapter. We covered a bunch of cryptography in more of an advanced understanding model. We looked at certificate authorities, certificate repositories. We looked at how to revoke our certificates. We looked at checking the status of our protocols and our certificates. We looked at the different types of certificates. We looked at PKI and its overall infrastructure it uses. Thank you. Thank you for joining me for this lecture review. If you have any questions or concerns, please feel free to reach out to me. Because I'm posting these videos on YouTube, if you leave questions in the comments, I will try to get to them as quickly as I can. However, these lectures are for my official courses. So again, ask questions if need be. If you're needing additional resources to cover this material, reach out also. I do have a good amount of material. I want to thank you and look forward to working with you throughout these video lectures. Thank you.